Welcome back. Now that we are done looking at some corollaries of the binomial theorem, let's go back to the theorem itself. And even though we're not going to provide a proof for it, I want to discuss some intuitive justification for this theorem. And in particular, I want you to understand why the binomial coefficient, namely the n choose j term in here, appears in this sum. So, to explain this point, let's look at a specific example, namely when n is equal to 3. And we're going to compute x plus y power 3 the good old-fashioned way. In other words, we're going to multiply x plus y by x plus y by x plus y without using the theorem. And this way we'll be able to see how these coefficients emerge. So first we're going to go from left to right and multiply the first two terms. So here we're going to get x times x plus x times y plus y times x plus y times y, and all of that must be multiplied by x plus y. Now again, we're going to perform the full multiplication of this first term by x plus y. So here is the result of this multiplication. So we have x times x times x, followed by x times y. These are the first two terms. And then we go to x times y times x plus x times y times y. These are the next two terms, and so on and so forth until the last term, which is y times y times y. So we end up with 9 terms, each of which is a product of 3 variables, each variable being either x or y. So notice some of the terms contain no y's like this one. Some of them contain one y like this one, and that one. Some of them contain two y's like this one, and this one. And this one at the end contains 3 y's. So I'm going to reorder these terms to group together the terms that have the same number of y's in them. So basically I ended up moving this term here over here. So that's really the only change I made in the order. And now we can simplify this expression a little bit to see how we get to this sum. So we look at the first term here. It's simply x cubed, and we add y power 0, which is 1, simply to make this term appear. Now we're going to look at those 3 terms together, and notice what they have in common is that they contain 2 occurrences of x and 1 occurrence of y. Of course, the order doesn't matter in the multiplication, so we can order them this way. So these terms are identical. We have 3 copies of them, and here is the next term in the sum. Similarly, for the next 3 terms, these have 2 occurrences of a y and 1 occurrence of x. So there's 3 copies of these identical products. Let's record that. And finally, the last term by itself is y cubed multiplied by 1. So we already saw, of course, that these 4 terms correspond to the 4 terms in the summation formula in the binomial theorem. What I want to discuss now is why these terms have the form that they have. So for example, why is it that the sum of the powers of x and y in each term is equal to n? Notice 3 plus 0, 2 plus 1, 1 plus 2, 0 plus 3. These all add up to n, which is 3 in this case. Well, that's not too surprising because remember we are multiplying 3 copies of the binomial. So when we multiply everything out, we're going to get a term, a variable from each one of these terms. So we have 3 terms, so we're going to get 3 copies of the variables x or y. And therefore, their powers will have to add up to 3 in every case. So that makes sense. Now, the more interesting question is, why do these terms get multiplied by n choose j, where j is the power of y? So let's focus on a particular value of the power of y, the particular value of j here. Notice when we form each one of these products of three variables, we have to pick a variable, an x or a y, from this binomial, and then we have to make another choice between x and y in this binomial, and similarly in that third binomial. So what is the smallest possible power of y we could have? Well, it is 0 if we decide not to pick any y's. So we pick an x from here, and an x here, and an x here. We get this term where the power of y is 0. And what is the largest possible power of y? Well, that's when you pick y in every binomial. So you pick a y here, a y here, and a y there. You got y power 3, or n in general. That explains this term. And of course, you can have all of the values between the minimum 0 and the maximum n. But why do we have this coefficient here? Well, now I think it should become clear. It's because how many ways are there to pick a given number of y's out of these n terms? Well, notice the order of the occurrences of y doesn't matter. What matters is how many of them do you pick. Well, we have n binomials, and for a particular value of j, we want to pick j copies of y. How many ways do we have to do that? Well, we have n choose j. Notice we are picking a subset of size j out of a total set of size n. And so that explains why the coefficient in front of these products is the number of, in this case, j combinations out of a set of n elements.